Hi class, we continue our study in chapter 14 by moving into our final section here. And this is going to be about maxima and minimum values. Okay, so what's the deal with this? It's a lot like it is with Calc 1, but we're expanding everything into the three-dimensional coordinate system here. So in this section we see how to use partial derivatives to locate maxima and minima of functions of two variables. Look at the hills and valleys you see in this graph here, and you can see what we're talking about. Like down here, this valley is the absolute maximum of the function. Here's a local minimum, compared to values around them. Here's a local max, and this up here has to be the absolute max. So we want to talk about methods for identifying these. Okay, so there are 2 points, A, B, where f has a local maxima, that is where f of a is larger than nearby values of f of x. The larger of these two values is what is called the absolute max. Likewise, f has 2 local minima, where f of a, b is smaller than nearby values, and the smaller of these two values is the absolute minima, and that's what we're seeing here. 2 maxes, 1 local, 1 absolute, 2 minimums, 1 local, 1 absolute. Okay, so just quick definition of these. A function of two variables has a local maximum at a, b if f of x, y is less than or equal to f of a, b, where x and y is near a, b, so around it. Okay. The flip side is with the local maximum. Here, same deal. If f of x, y is greater than or equal to f of a, b, where x, y is all those values around a, b, then f has a local max at a, b. All right, so how do we find these local max? This leads us to theorem number 2 here. If f has a local maximum or minimum at a, comma b, and the first order partial derivatives of f exist there, then you will have the following. The partial derivative of x evaluated at a, b is equal to 0, and the partial derivative of y evaluated at a, b is also equal to 0. Okay, a point a, b is called a critical point or a stationary point of f if f, the partial derivative of f with respect to x at ab is equal to 0, and at the same time the partial derivative of f of y evaluated at ab is equal to 0. All right, or if one of these partial derivatives do not exist. So it's just like Calc 1, right? Like you find critical values by seeing where the derivative is equal to 0. Here it's kind of the same concept, but we're looking where both partial derivatives equal 0. Okay. So theorem 2 says that if f has a local maximum or minimum of ab, then ab is a critical point of f. All right, however, as in single variable calculus, not all critical points arise to maxima or minima. Okay, at critical values, a function could have a local max or a local min or neither. All right, let's do an example here. So we have this function, f of x, y is equal to x squared plus y squared minus 2x minus 6y plus 14. If we look at the partial derivatives, right, the partial derivative with respect to x would then just be 2x minus 2, and the partial derivative of y with respect partial derivative of f with respect to y is just equal to 2y minus 6. So these partial derivatives are equal to 0 when x is equal to 1 and at the same time y is equal to 3. So you just set these equal to 0 and solve. So the only critical point here is 1 comma 3. All right, so you can actually complete the square on this and you can see this right here. So it looks like, this is kind of some type of formula perhaps that we've seen. So you can see the shape here and it makes sense. So since x minus 1 squared is always greater than or equal to 0 and y minus 3 squared is always greater than or equal to 0, we have this function f of x comma y is always greater than or equal to 4 for values of x and y. So therefore what's going on here is that point that we found, this 1 comma 3, has to be a local minimum. And in fact, it's actually looking at the graph, it's the absolute minimum of f. So this can be confirmed geometrically from the graph that you see here, and that is the shape that formula tells us, and we can see that the vertex is the point 1 comma 3 comma 4. Okay, so the next one here, the following test is analogous to the second derivative test for functions of one variable. So now here's the second derivative test for when we have functions of more than a single variable. Okay, for two variables. Suppose the second partial derivative of f's are continuous on a disk, and that disk is centered at AB. And suppose that the partial derivative of f with respect to x is equal to 0, and the partial derivative of f with respect to y is also equal to 0. Okay, so AB is a critical point. Then we define this value d. Okay, and d is equal to a function of a and b. Okay, this critical point. and it's equal to the following formula. Okay, it's a little bit complicated. The second partial derivative with respect to x twice, evaluated at that point, times the second partial derivative of y twice, evaluated at that point, minus the partial derivative of x and then partial derivative of y, evaluated at ab squared. If you follow this formula, okay, they're going to have the following rules. If this value is greater than 0 and the second partial with respect to x twice is also greater than 0, then this f of ab is a local minimum. If this is greater than 0 but the second partial derivative with respect to x twice is less than 0, we have a local maximum. If this d value is less than 0, it's neither a maximum or a minimum. In this case, this point AB is called a saddle point of f, and the graph of f crosses its tangent plane at AB. Okay, so this right here is going to help us tell if it's a local max or min. And so the formula looks a little crazy, but it's actually not that bad. All right, now let's talk about absolute minimum and minimum values. Absolute maximum and minimum values, excuse me. All right, for a function f of one variable, the extreme value theorem says that if f is continuous on a closed interval a to b, then f has an absolute minimum value and an absolute maximum value. According to the closed interval method, okay, we'll talk about that, we found these by evaluating f not only at the critical numbers, but also at the endpoints of AB. All right, there is a similar situation for functions of two variables. Just as a closed interval contains its endpoint, a closed set in R squared is one that contains all the boundary points. So the problem with this is what does that R squared look like? And you'll see when we go to evaluate finding maximum, minimum, it's a little bit more complicated. So a boundary point of D is the point AB such that every disk with center AB contains points in D and also points not in D. So for instance, this disk, okay, that we define as the points x, y, such that x squared plus y squared is less than or equal to 1, which contains all the points on or inside this circle, right, centered at 0 with radius 1. This is a closed set because it contains all the boundary points, okay, which are points on the circle. All right, but even if one point on the boundary curve were omitted, then the set would not be closed. Like this is sets that are closed. These are sets that are not closed. This is just one point. So a bounded set in R squared is one that is contained within some disk, so like this. In other words, it is finite in extent. Then in terms of closed and bounded sets, we can state the following counterpart of the extreme value theorem in two dimensions. Okay, so if f is continuous on a closed bounded set D in R squared, then f attains an absolute maximum value, which we denote as f of x1, y1, and an absolute minimum value, f of x2, y2, at some points. Okay, so now it's going to be up to us now to find those points and find the max and mins. Okay, so to find the extreme values guaranteed by this theorem, we note that by theorem 2, the first theorem of this lecture, if f has an extreme value at this point x1, y1, then x1, y1 is either a critical point of f or a boundary point on our disk D. Okay, so thus we have the following extension of the closed interval method. Okay, so to find the absolute maximum minimum values of a continuous function f on a closed bounded set D, first thing you're going to do is you're going to find the values of f at the critical points of f in that D. Then you're going to find the extreme values of f on the boundary of D. And the largest of those values in step 1 and 2 is the absolute maximum value, and the smallest is the absolute minimum value. All right, so we'll do this one example, and it'll illustrate everything we've been talking about. So let's find the absolute maximum minimum values of this function. F of xy is equal to x squared minus 2xy plus 2y on this rectangle D, which is given by the points x, y. X is bounded between 0 and 3, and y is bounded between 0 and 2. So I'm just going to skip ahead for a second. This is that rectangle. X is bounded between 0 and 3, and y is bounded between 0 and 2. So we want to find the maximum value of this function, whatever it looks like, only on this bounded rectangle right here. Okay? All right, so looking at f is a polynomial. It is continuous on the closed bounded rectangle D. So theorem 8 tells us there's both an absolute max and an absolute min. So we got to find those. So according to step 1, okay, we first find the critical points. So looking back here, first find the critical values. Okay, so these occur, what you're going to do is you're going to find the partial derivatives of this function. So the partial derivative with respect to x is 2x minus 2y. Partial derivative of y is minus 2x plus 2. So you have to solve this, right? So the first thing you're going to do is you're going to solve this, okay, because it just has a single variable, and you'll get x is equal to 1. And then what you'll do is you'll take that 1 and you'll plug it in here for x, and you'll find the value of y. Okay, so the only critical value is the 0.11. All right, and the value of f there, if you plug 1, 1 into our function for x and y here, you're going to get 1. All right, so in step 2, we look at the values of f. So looking back at step 2 here, find the extreme values of f on the boundaries of D. So I got to look at the extreme values on these boundaries. Okay. In step 2, we look at the values of f on the boundaries of D, which consist of 4 line segments. Okay, we have this line segment here, this line segment here, this line segment here, and this line segment here. Okay, so what's interesting here is notice on this line segment, y doesn't vary, only x does. On this line segment, only y varies. On this line segment here, only x varies. And on this line segment here, only y varies. So we're going to use that to help us out to find the extreme values or the max and min values on the boundaries. Okay, so on L1, as I said, you have y is equal to 0. So plug that in. Okay, plug that into your function, and you end up just getting everything with the y goes away, and you end up just getting x squared. So we know this is an increasing function of x, so its minimum value occurs at 0, 0, and its maximum value occurs at 3, 0, which is 9. On L2, so going back, L2, x is constant, it's equal to 3. Okay, so we're going to plug that into our function, so we get 9 minus 2y, but remember, y only goes from 0 to 2. Okay, here it only went from 0 to 3. So this is a decreasing function of y, so its maximum value is f of 3, 0, which is 9, and its minimum value is f of 3, 2, which is equal to 1. On L3, we notice going back, L3, y is constant at equal to 2. So we're going to plug that into our function, and we get the following. Okay, we get x squared minus 4x plus 4. So just observe that that's just very simply x minus 2 squared. We see that the minimum value of the function is f of 2, 2, which is 0, and the maximum is f of 0, 2, which is 4. And finally, L4, x is equal to 0. And when you plug 0 in for x, you just get y is equal to 2y. So that's an increasing function. So the maximum value occurs at f of 0, 2, which is 4, and the minimum value 0, 0, which is equal to 0. So just look, on the boundary, the minimum value we got is 0, and the maximum value is 9. So what that also means is that this 0.11, while it's a critical point, is just a relative max, or relative extrema, excuse me. So looking here, we can compare these values with the value of f11, which is equal to 1 at the critical point, and conclude that the absolute maximum value on this function occurs at the point 3, 0, which is 9, and the absolute minimum value of this function occurs at 0, 0, which is also the same as 2, 2, which is 0. And you can see that from the graph here. All right, I hope that helped as a quick introduction to maximum and minimum values in 3 dimensions.